Hello, welcome to this awesome event. I was waiting for it when I was still an ambassador, but I was expecting also to become a Microsoft employee. I have some titles. The program is amazing if you haven't realized that, and it helps you build your career, not necessarily being part of Microsoft as the end goal, but it helped me a lot during all my career as I've been a software developer, or better said, full stack software engineer for the past almost 5 years, which was an amazing journey. Now I'm at Microsoft in the CE team for Azure and AI consulting, which is also amazing. And today I'll talk to you about machine learning, an introduction to AI, and focus on this part of machine learning we're using Python. And from Python, because Microsoft loves PyTorch, I use PyTorch, and I also love PyTorch, which is a really nice. TensorFlow is also cool, but it's, as you say, coding style preference. So let's dive into it. Today we'll talk about what is artificial intelligence, because you've heard a lot of this buzzword lately. When you should use machine learning, and we'll see what's the difference between machine learning and AI, the model building process, some tools for it, because it doesn't have to be complicated. We'll see that nowadays a lot of things are pick and use, so we don't necessarily have to do everything ourselves. Of course, we have to specialize for specific tasks, we have to go beyond, but we have at least a start, which is really nice. What means NLP, natural language processing, because it sounds complicated, but it's a lot easier when we can explain yourself. And then building neural networks with PyTorch, so cool stuff. So let's begin with what is artificial intelligence. Well, we see in the beginning 3 terms, or 3 abbreviations, better said, AI, ML, and DL, which means that we can't necessarily put an equal sign between them. Maybe we can put some inclusion signs between them. So in general, AI is a technique that enables computers to mimic human intelligence, or better said, we make our processes of solving a problem more abstract, that they can be explained to the machine, and then the machines help us because it can do those processes a lot faster than us. But the initial step is making sure that we fully understand the process so we can fully explain it to the machine. Now, moving to machine learning, this is a subset of techniques. So ML is in AI, in which we do a better type of problem solving called learning by examples usually, or redoing some information. So the way humans learn usually is by examples or by experience. So we are either told something or we experience something and we develop techniques. AI is a more broader concept. So for example, even the game theory in which we can explain a game, let's say chess, let's say backgammon, let's say any game, it's AI and uses AI techniques to solve the problems. But then we go deeper to learning by example or by learning by experience, we're going to the ML field. And then going even deeper, deep learning is a subset of machine learning in which those algorithms are not necessarily only learning by something, is using a concept called artificial neural networks, which try to mimic the way our brain is built by trying to replicate neurons and the links between them. So we're trying to replicate as much as we can about what we know about ourselves and our brain and our way of thinking, which is nice because we'll understand ourselves better in the end. Now, machine learning usually is about finding and exploiting patterns in data. So data is the main pillar of what we want to do in ML. Then it will replace how we write code, because let's say we want to build an application, we have to write a lot of code. A lot of code is standard for routings, for human interaction, for events, and so on. And then we finally solve the problem that we want to. Now, doing ML will replace the writing the actual code, because we don't necessarily know the exact solution of our problem, but we know the, let's say, steps we need to take about it, and then we have to adapt some parameters, we have to adapt some, let's say, ifs, let's add some fors, and so on. So this will happen on the machine side by using our data. in general, the more data we have, the better the algorithms will behave. And why I'm saying algorithms is because in general, there is no magical solution for a problem. We have to try different approaches. We have to try different parameters, or let the machine try a lot of parameters until we have the perfect solution. And then when we're using machine learning, it has to start with a question. And the question in general is, do we really need machine learning? Because if the answer to that is no, then we shouldn't use machine learning. Yes, it is a cool concept, but if a standard algorithm may be able to help us, that's the better way, because we'll talk a bit later about this. Machine learning needs to be ethical, and it needs, on the ethical side, to be explainable. So when we build something for the real world, I say question, Python is better than Java for AI, ML, right? Depends, because Python is the thing that we're using because we have a lot of cool tools. So if we're talking about is Java better than C, depends what you want to do. If you want to write an app fast, then probably Java is better because it has a lot of libraries, a lot of frameworks, and so on, so you build faster. But if we go back to speed, probably C is better in case of run speed, in case of threading, in case of memory management. So it all depends on your question. For some things, we'll see that MLNet, which is the C# flavor of some known Python frameworks, runs faster, but it doesn't have all the tools. So it depends on what you want to do. If you want to explore the whole thing, go with Python first, because it has a lot of things you can try with, frameworks, libs, and so on. But then if you want to find the fastest one, seek your problem, for example, simple classification, and then see benchmarks which one is faster. So if you want to solve in the fastest way, see for the specific problem which one is faster, and then you'll see maybe it's Java, maybe it's Python, maybe it's R, maybe it's MLNet, who knows? So you need to try. Python is called de facto because a lot of people are using it because it's simple to use, it's simple to write, and a lot of people are doing it. But in general, you need to focus on a specific thing to see which one is better. And then again, it comes if it's easier for you to write in that specific language, because for me, if you ask me to write Dart or Rust, I'm really bad at it. Even if it's the best language out there, I can't. So for me, it will be faster to run Python. I hope that answers. And now, the cases when we should use machine learning. We have some standard cases, regression, in general, when our question is how much, how many, because we are trying to say, okay, what's the question? Classification, which label does it have? Is it a desk? Is it a computer? Is it the dog that was barking a few moments ago? Clustering, do we have some particular relationship between things? Are they belonging to some groups? Anomaly detection, is it weird? Like we're seeing the temperature outside and we have a 10-degree drop, was it weird? We have to see if it was an anomaly or not. And then recommendation, what option should I use? So recommendation, I think, is in everyone's life. When we see recommendation of friends on Facebook, we see recommendation of content on Instagram, we see recommendation of products on online shops like Amazon and so on. So we have a lot of machine learning, or in general artificial intelligence in our life, but we're not really realizing it because it's there. And then AI should be classified in supervised learning, which means that in general we hold the universal truth. So for example, we know the answer for the problem, we know how many or how much things we have, or we know what's the labor for that, and the machine has to guess. And then for the other is called unsupervised learning, which means that we don't necessarily know the truth, so we want some groups in terms of clustering, but we don't necessarily know what groups. Maybe we have something we want to look about. Like for example, if we look at cars today, we want to see cars by color. So we tell to the machine that, okay, we want to see color, and then it builds us the groups. Maybe next day we want to see by brand. Maybe next day we want to see by fuel type, and so on. So in clustering and in general in unsupervised learning, we don't necessarily know exactly what we're looking for, but we have enough data and we have a criterion to which to look at things. I hope it makes sense. Now, moving to our question specific for this workshop, what what we want to see is that, okay, I have a data set about news, and I want to see in which category this news falls. So this is a standard data set. It's called AG News. We'll see it later in details, and in general it holds news in some categories, and we want to see if it's some of those categories. A good problem, because we're tackling the NLP sphere, so natural language processing, in which words have meanings, which is a little bit more complicated than, for example, predicting the price of a house, where we have only numbers, and we'll see why it's that. So, okay, we have the question that we want to answer. So what's next? Well, we have a process, which luckily it's a standard process in which we build the actual model. And it has 4 steps in general: the data exploration, training the model, testing the model, and deploying the model. And it's a circular process, because we get more data. Maybe we want to update the model. Maybe frameworks evolve and they move faster and they provide better data. Who knows? So in general, those are the 4 steps that are going to be going through a feedback loop and repeating again and again when time comes. You don't have to rush. So for the data exploration side is finding, selecting, or creating data, because sometimes we have data on the internet, sometimes we don't. Sometimes we can get data from actual institutions. For example, if we're looking for medical data, maybe some hospitals can provide it, or we have to create data. For example, right now I'm researching something about harmful content in social media. So the best thing to do was get actual social media content, tweets, for example, and then label them myself, or label them with the help of our research team. So I'm creating data. If I found a data set on the internet, it's found. Or sometimes, for example, if you go on Kaggle, which is an amazing opportunity if you want to start in the ML or data science world in general, on Kaggle you'll find a lot of data sets, because there you have challenges, there you have problems, there you have tutorials, so you don't necessarily need to know anything. You just need the desire to start. And then after we have our data, which you'll see that it's a really complicated process in general, we have to apply some pre-processing, which means curating the data, normalization of the data. So for example, we have prices in different currencies. Maybe we have multiple alphabets and we need to stick on only one, and so on. And then, which is really important, are the ethical considerations, because ethics is a thing that is not new, but it wasn't focused enough lately. So whenever we're building a solution, we need to consider the ethical considerations of what we're doing, what can be used for. And when we're using AI, we need to be extra cautious, because maybe our algorithm has 1 appliance for good and 4 appliances for bad things, and for that we need to reconsider, and starting from the data. I think you all know the example of the automated HR machine that was hiring people. I think it was at Amazon data or something like that, Amazon, Google, a big company nevertheless. So it had a lot of data, a lot of experience, a lot of history. So the data quantity was not the problem. And then the machine thought that, because it became biased, that in general men should be hired because the percent of men was more than women in that company. And that was the issue, because it biased on a single dimension of the data, the number of people of that gender. And that's an issue, because when you have multiple dimensions of your data, so multiple characteristics of people, sometimes your model might pick the easy way out. So for example, if we have only 2 values or very few values, 2-3 values, the model might focus on that particular feature because it's way easier than going through 1,000 values for something. So it might put more weight into that. And then you have to think, okay, I have all those features. Let's see each of them. If this one may fall into bias, first I need to watch it, and then I need to see what's happening if it falls into bias. Can I still use the model or not? So those are an example of ethical considerations. But we have many ways to mitigate them. We have people specialized on ethics, people specialized on AI ethics, so we have a community to help us. Then finally, moving to the fun part is the training of the model, which means we need to apply some learning algorithms, which are a lot. Luckily for us, for any problem, we have a lot of options to choose from, starting from the actual algorithm, not the parameters, and then selecting the perfect model. When we'll see frameworks, we'll see that we have something called AutoML, automatic machine learning, in which we provide the data, we provide some resources, we provide some time constraints, and then the framework helps us by building multiple models, and then we can choose the one that we like. So for example, for a given problem, let's say our classification problem, finding news, the model will train 20 models in the given time, 20 different models with different parameters or nature, and then we'll have to choose from them, which is cool. And now, finally training the model, but questioning what's the best model for them, we have this cheat sheet, and in general we'll have a lot of cheat sheets on the internet, because for example, if you go to text analysis, the cheat sheet tells us, okay, we have to extract Ngrams or do feature hashing or pre-process text or word to vec and so on. So for regression, we have all those cool algorithms. For clustering, usually k-means. For multi-class classification, all those. For two-class classification, all those. For image classification, this one. For anomaly detection, these ones, and so on. But you'll see in general, when you research the internet for papers on a topic, that you'll have 3, 4, 5, 20 candidates if it's a standard problem. The standard problems usually are classification and regression. So for those, there are so many algorithms. Now for image classification, we're getting a lot more, and so on. So you'll have resources, and they're on the internet, just waiting for you. And now that we have the model, we have to test it. What's really important in testing is testing with unseen data. Unseen data means that we train the model or on some data that we have the same structure as the trained data will have the same structure as the test data, but won't necessarily be the same cases. So for example, if we're looking for prices, for the prices of a house, we have the same type of houses, same number of rooms, same number of distance from the city center, same number of, I don't know, previous owners. But then when we'll test the data, maybe we don't have the exact same combination, or it's preferred to not have the exact same combination of values. So for example, if we know that always a three rooms apartment near the city center costs that, if you provide it again with a three room apartment near the city center, then we'll get the exact same result, and then it's not necessarily relevant for us. So it's important that we have different data when we test and then we train. Because if you test on trained data, you'll get something called overfitting, because the model is usually fit for the training data, and then the model will exactly give you the right solution for the trained data, but then when you test in the real world, it will have really weird behavior. And then it's really important to explain the model. So for example, if we go to a more complex thing than houses or our predicting the label, we go to the bank. Let's say we want to build an automatic model for the banks that helps them with loaning. And then when someone tries to obtain a loan, it pulls all the data that's required, it goes into our model, and then our model says yes or no. Now, if you answer yes, you'll need to explain to the bank why you said yes and they should give the money. And then if you say no, you'll have to explain to the person why you said no and he can't loan money. So it's important. How will you know which machine learning algorithm to choose for a classification problem? We have in the literature best things to try, but in general it's trial and error. So you know from the literature that from this data, the best one will be this algorithm with this pre-processing, because it worked on similar data. But if you are on totally new data, for example, I don't know, there's no classification for images that have HoloLenses, because HoloLenses are new. So we don't know that a classifier will be able to pick a HoloLens from a VR machine or from regular glasses, right? So you know that, okay, for those types of image classifications, you have those types of models, 2, 3, 4, 5, which are in general the best for this type of problem, and you try them. In general, when you see a paper, a research paper, you'll see that, okay, we tried this model and this model and this model. We expected them to work because we saw them in different papers. And then when we tried, we had those results. Sometimes you get the, as expected, this one was the best model as it was previously. But sometimes you get like, we expected this one to be the best one, but it was not. Because sometimes, because your data is different than the previous one, it's new, it's a new problem, you'll see some changes. It was my case when we tried on different data that the best model expected wasn't the best, but the second best was for this type of data. So in general, it's trial and error. Luckily, you can try on smaller data, so you can do a, I don't know, 10 minute sample of training, see how the results look. If they look promising, you try on the whole data, and then you're good to go. But in general, you shouldn't try only one model. You should try maybe at least 3, so you have some comparisons. You can go with really simple models. For classification, we go with classical ML. In general, we go, I don't know, SVMs or logistic regression, which is really simple and fast. And then we try some neural nets, we try transformers, we try BLSTMs and so on. So in general, you should have 2 or 3. Two is the absolute minimum to see results, but in general, you should have 3 different algorithms to pick. And in general, for a problem, you'll have literature to see similar problems how they are solved. Okay, hope that answers. Do you think it's possible to code the AI to learn ethics during learning from human behavior? Think it's possible? Yes. Think it's easy? No. Because ethics change from time to time, and that's important. And then it's easier to do rules, like some standard rules that you don't have that, you don't do this, if you see this word, like we have profanity filters. Right now I'm trying to do harmful speech detection, which on one side is really easy. Yeah, Facebook AI mates. Yeah, and some Twitter also. I think Microsoft did a bot on Twitter. It was first started in China, if I'm not wrong, and people were really polite, and you could call the bot. It wasn't necessarily only looking for specific hashtags. You could like talk the bot like you talk a user, and then he would learn from you. And in China was super polite. And then when it was open to the whole world, the trolls made it super racist and super offensive in general in a few days, because it's really easy. Like in general, we have profanity filters which work on, I don't know, 90% of the cases, because in general for harmful speech you'll have some keywords, but then you have some more subtle harmful speech. That's what I'm looking for. So you're welcome. So ethics will be kind of hard if the model is not learning, and then if it's learning, it's important from who to learn from. So for AI ethics, if you use AI, I think it's a bit hard. So not necessarily for one researcher, but if you have a whole team looking for that, it would be good. If you start with some rules and you want to limit on some cases, then it's really possible. Okay, I know what's wrong and what's right thanks to the that's the main question. Well, we don't know what's right and wrong. So good and bad are some things we came up with. So we defined what's good and we defined what's bad. That's where we stop. So if you want to see what's truly good and what's truly right, we have to put two different sides on opposition, and that's subjective. AI should learn objective things. So if we stick to the thing, okay, this is good and this is bad, I define this as good, I define this as bad, then AI can learn that. But if you want to see what's truly right and what's truly wrong, we need to do data analytics, not necessarily AI. Hope that answers. How can we limit AI to only local information and avoid the whole trolling thing? Exactly how you answered. You tell it, don't look at things on the internet. If someone calls you, reject it. You learn only from what we tell you. We manually filter the data, or we automatically filter the data for you, and then you learn from it. But if you build the model to have live feedback, then you should expect trolls, because that's how the internet it goes. Yeah, if you program the AI not to do something it's not really AI, that's debatable. Our parents told us to not pick our noses. Maybe we respect that, maybe we don't, but sometimes it builds more than just not doing it because I don't consider it. So it's really, we are in the philosophy side here. Like AI, as I said, is trying to build something that is close to the human behavior. We don't really truly understand ourselves. So we don't truly understand the human nature. We don't truly understand the way the brain works. Like, we understand some electrical properties, but we don't necessarily understand more. So building AI close to us, it's possible. But first, we need to truly understand what's us, okay? Yeah, ignore bad words. But we do that also in the real world. Like, for example, I ignore some things. Am I not really AI? And so on. So it's on the really debatable side, those questions. Now that we have the ability to explain things, let's dive deeper into deploying a model. And this is important because we want to share. It's important in general to share things. So I encourage you, when you do projects, if possible, post them on GitHub. Maybe nobody will look, maybe someone will look. So when they'll search for things, they'll find yours and they'll thank you. Not necessarily public, but inside they'll help you. But in general, we want to build things that help others. So we want to deploy the model somewhere on the internet, or maybe somewhere on some site where they can access it and so on. In general, we have tools for that. You can do classical deployments. Azure ML provides you with some really easy things. You just do some drag and drops and then your model is on the internet. Or if you build the model inside Azure ML, it's even easier. But for example, if we build the model, ML, deep ML or not, we can save the model, load it on the Azure ML, and then it will build an API from us, which is just load the model, run the test, return the answer. That's it, which is really cool. And then it's important that humans oversight the behavior of the AI, because maybe, as I said, we did an overfit. On training was really good, and then on test it was really bad. So for example, that means that our AI is not necessarily helping people, maybe it's doing the reverse. So it's important to have some feedback for the model. Doesn't have to be public deployment, it could be also private deployment, which means our research groups or our university. And now that we have all these, let's see what's NLP, what's language processing, and what we can use to build those. So for example, we have Python, which usually has the most heat because it's used a lot. And then for libraries, we highlight PyTorch, TensorFlow, and scikit-learn. There are a lot more used for ML, but those are just really top when I looked. For editors, Jupyter Notebooks or VS Code. I'll use VS Code because it integrates really nice. For R, we have those. For the others, we have, for example, JavaScript with TensorFlow.js. Of course, we have also Java. We have C# with MLNet. And MLNet is starting to gain some ground. It's faster on some classification tasks and regression with at least 25%, which is nice if you're in a hurry. And then we have AutoML, which is really cool. We have a lot of providers. Microsoft has some, Google has some, scikit-learn has some. So you have open source, open cloud, related to cloud, related to subscription ones, and a lot more providers will come with them. And this helps us to decide where picking the model and picking the parameters. But it doesn't save us from providing data, which is usually the hardest part. And it's a good start. So if you don't know what to pick, what to do, you pick an AutoML, you see what models it's using, and then you can pick the best model and toy with it yourself a little bit more, because all AutoML frameworks provide you with some explanations, why they pick those models, why they think that's good, what transformations they use, what parameters they use, so you can pick up the work, rerun it, and then improve it. So that's a really good start. Now, how does NLP work? Well, machines don't understand words. If you did like lower level programming in university or in school, you remember that strings or arrays of characters are in general some representations of numbers in a way that we can read. So for example, each character has behind it a number. So if we think ASCII, we have 255 or 256 characters in which we have associations for small letters, uppercase letters, some symbols, some signs. But they're numbers because machines can only work with numbers, and we gave some associations between characters and numbers. Then if we go a bit further, we go to strings. That means that we have a number of characters separated by some other characters which have some meaning. And then it comes to the meaning side, which is the more complicated thing. Words have meanings because we learned those words and we associated those meanings to those words. And then when it comes to languages, it's even more complicated because for the same object, for the same action, for the same behavior, we have a different word in different languages. Sometimes they match when you generally have a common root, like for the all Latinic languages in the Latin family, you'll have similar forms usually for the same word, but still different. So for the machine, it's really weird that a concept is represented in different numbers. Because, for example, we can build a really huge number with that representation of the word. So for the same meaning, so let's take, for example, I don't know, mouse. Then in different languages, it will have really different representations, and then it will be confusing for the machine. So we need to start explaining what the word means to the machine, and for that we have, let's say, the standard pipeline. So first we start with sentence or word tokenizations. We need to split what we want to explain in different tokens. So for example, when we're talking, we're looking for either words or groupings of words. They give meaning. So let's break the whole sentence by space and say that each token, each word is important. Then we do lemmatization and stemming. This is an optional phase, which means that we return the words to a more first form. So for example, all tenses from the verbs are removed, or all prefixes and suffixes are removed. This is lemmatization and stemming. Then we remove stop words. For us, it's important to see the difference between a lion and the lion. But in general, the word the doesn't have any power in English because it's really used a lot. So it will be considered a stop word, and usually it's removed. If we do sentiment analysis, it's important to see the difference between a lion and the lion, because the might add extra power to the sentiment. But in general, we'll remove them for the variety of tasks. But again, this is also an optional step. Then we do spell check, optional, lowercase, optional, regular expression, optional, remove special characters, optional. So until now, the only important step that is mandatory is tokenization. Maybe the whole sentence is a token for you, but it's still tokenization. Then we have Ngrams, which is optional, which means that we don't necessarily consider each individual token as the unit of work. So not necessarily every particular word, but maybe we consider groupings of 2, of 3, of 5, of n. So this is why it's called Ngram. And then is the part of text embedding. Embedding is something really powerful because it moves from, I don't know, characters for the computer to, okay, this means something. And embedding is starting from the simple bag of words, which means that we associate words in a sentence with do they appear or not, and then for that we have an encoding. To really complicated things like we try to do with words and meanings, we try to represent the words in a vector space with a lot of mathematics to give similar words, similar meanings. So for example, if we go to, let's see, medieval royalty, we have king, queen, really close, knight kind of close to them, squire kind of close to them, but still, if we keep those and then let's say castle, castle is a bit further than knight because knight is a human, but castle is something that's close to the kings and queens. But then if we throw a random word like plane, it should be really, 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 really far away, somewhere in the space, but really far away from them. And then how do we do that? Well, with mathematics, we consider some things. Can we consider the form of the word, like what characters they have? Well, not, because king and queen don't necessarily have too many characters in common, doesn't knight also, castle, and so on. So for that, we'll do a machine learning of itself to build that vector space. So embeddings can start from really simple to bag of words to really complicated, which are machine learning things of their own. So we can also use a classification algorithm to build an embedding. What math is used for AI probability? Well, all of it. Starting from probabilities, which is the simplest thing to build probabilistic models. When you do embeddings, you'll need a combination of linear algebra to make sure that you can move from a space to another. But you also need, I don't know how it's called in English, analytics maths, where you'll need gradients, first form, second form, and so on. So if you do ML, you don't escape maths. You'll do more maths than coding. So right now I'm focusing on the maths part for doing AI. Now let's do this. And let's see how we do this. I'll stop sharing this one and start sharing the notebook just to show you how easy it is. By the way, this is a tutorial. I haven't done anything. I just made sure to make sure that it runs. So this is the tutorial from PyTorch called text classification with AG News, and then we'll see what steps it is. First is the import step. As we see, we import Torch for PyTorch, data sets, utils, vocabularies, and some things for displaying. As you see, we have all the functionality that we need in those 4 lines, which is really cool. I will run it now to make sure that I'm not cheating. I run everything to make sure that we stay in time. And then we'll use this data set, and in general will be 2 splits, the training and the test. As I said, we should train only on some data and test on some other data. And let's see how our data looks. So we have something that's a text, we can read it, it's really cool, which means that the computer can't read it, so it's really bad. Will we need discrete mathematics too? Yes, the computer can go with continuous mathematics, so we'll do the calculus and the theory in continuous mathematics, and we'll see how it goes into discrete mathematics. So for example, it'd be really cool if the computer would be able to do a limit, but we can't, so we'll have to go with the Taylor expansion, or if you want to do some, I don't know, integration and so on, but the computer can't do it, so we need to think some other ways to do it. But yeah, we want to think in continuous mathematics because for us the data is infinite and continuous, but the computer can go only in discrete space, so we have only numbers. And then going back to our data, we have the text. We do understand, the computer doesn't, so we'll have to work on this. And we have the category, we kind of understand it and the computer understands it, so this is good. As we said, we are in classification, so we are in supervised learning, so we know the absolute truth. So this is the class the computer should be getting to guessing. Well, not guessing, but learning. Now there's some pre-processing. As I said, we need to create tokens. In this, we'll do tokens with the default split, and we'll see how the vocabulary looks. As you can see, we have some basic representation for the tokens. We have a lot of tokens in the vocabulary, and then these are more labels, not necessarily something new. And then what's really important is building iterators, or in general the concept of batches, because sometimes the model can't or shouldn't work with the whole data set, and it should take in batches. Or maybe we can go even deeper. We give batches of a sentence. So for example, we want to train on a sentence, but we give batches of it. So for example, for this sentence, I'll give you multiple batches. The first batch has a meaning, the second batch has another meaning, and so on. And this thing you see is the eternal discussion between what should we use, CPU or GPU, and then the question goes APU lately. Well, if you got your GPU before 2019, you can use your GPU. If you didn't, then you probably are not having a GPU, so you can't use it. So you'll have to use a mixture of both. But this is, again, recent events. And here we'll build those batches. Don't worry, nobody knows how to do this. We all copy it from the internet. We'll just play with the type, or maybe we'll play with the way the batch is sent. Maybe we don't want to send the batch fully, maybe we want to skip some tokens, maybe you want to do some things. But in general, you don't have to worry, you have a lot of code on the internet, you should be able to read it and hopefully also understand it. So as you can see, my loader will do the training data, which is the corpus only on train. The batch size will be 8. I won't shuffle the data and I won't collate it in some really specific way. And now the interesting part is the model itself, of course. The text classification model, which has a layer, which is embedding, has another layer, which is a linear, and then that's it. So our really complicated neural network has only 2 layers, or basically one functional layer, which is the linear, and then also the embedding. We'll see a picture with those explained. So what this model will do a forward, and then it will do a gradient descent, which is a workshop of its own or a lecture of its own. We won't go into details about gradient descent. But in general, it will move from the information from start to end. We'll get some feedback at the end, and then propagate that feedback starting from the bottom to the beginning to make sure that the next run is better, or at least different, and this process will go on and on until it's the end. Of course, we have different models that are recurrent, that go like this, and so on. We have a diversity of models, but in general, we start from something, we get some feedback, we apply that feedback to our network, and then we continue the process as we know it. So as I said, back of words is really nice embedding because it's really simple. So we have this type of representation for a sentence. And then if we go to the word level, we have that bird is here, bird is here, bird is here. So we'll do 1, 1, 1, and so on, depending on how we do. And this is our neural network. This is the input. This is the input already embedded. It goes to this linear, and then it goes to the output. As you see, linear is just summation. As we have the symbol for summation, it means that our linear layer takes all the inputs, so takes all the words, for example, and then applies some weights on them. So for example, let's go to this sentence. The bird is the word, okay? We know that for the first word, we put 02 importance. For the second word, we put 03 importance, and then so on. So we sum the embedding multiplied by the weights of each part of the embedding, and then summing this with some number, we get a number, and then this number goes at the output, and then the output gets tested against the actual output, and then it updates the weights back. So if it started with 2, 3, I don't know, 2, 3, 4, I don't know if it sums to 1 or not, but then it will update to 1, 3, 2, 1, 2, and so on, until the end when it gets the weights for the actual important. Now, this is a really simple model. I think it was in 75 or 76 presented, which was a lot of time ago, and we went a lot over that, but it's still good. We'll see that this model behaves really good. So we'll do this. The embedding size is 64. We build the model. We do the evaluation with gradients and blah, blah, blah. You'll get to understand this one day. And then we do some metrics, which is important because sometimes we don't pick the model based on a single metric. Maybe we pick the model on a combination of metrics. So for example, we have precision, accuracy, recall, F1, and a lot of more metrics. So maybe we don't pick only on accuracy, which means that it's recognizing right. Maybe we pick on recall, which means how able it is to recognize out of the whole examples. And running the code is decently easy. We build loaders for everything, and basically we do train. So for each epoch, we do train. This is the complicated part. You have functions that will do the training for you. And as you can see, it's doing epoch 1 with some batches, and it has this accuracy, then it grows a bit more, then it grows a bit more at the end. And then the next one will start with this model already. It will get different, a different shuffle of data, so it upgrades a bit, and then it goes back. Why? Because probably it overfitted, and then when testing it have to go back. So then again we train. As you can see, we have a huge jump from this to this. So the model probably started at 050 or 060, and then after some training it become 068, and then it jumped to 085, and then 078. So the difference between those two is not that much, and then as we can see at the end we get this one. So it's not for more epochs, it's not necessarily getting that good. It will stabilize at some moment. It means that it reached saturation, probably is the word. It had enough examples, so it can't learn anymore. Like in the real world, if you train a machine, a car, let's say we do a self-driving car, if we train for the same road for 10 months, it will probably learn to drive on that road after 1 month. So 1 month is enough. And in general, in machine learning, we have some parameters or some conditions that if the difference between 2 consecutive epochs is negligible, like maybe the decimal after this or maybe even this one, we stop. Because we don't want to waste more time, we don't want to waste more resources, we want to see how it's really behaving. Okay? So this is what we can do. At some point your model will stop, but of course, if your model is really complex, because we're doing just a linear, if your model is really complex, the amount of data needed to make sure that the model learns enough is greater. And then let's see how it goes. So our test accuracy is 90%, almost 91%, which is really good. And let's see how it goes to the real world testing. In here we have those labels. We put our text, and this is the text. Although I did this workshop a few times, I still don't remember if it predicts good or not. So, and we also put it on CPU to make sure that our model works on both. Because when you train, it's recommended to use the most powerful thing you have, because you want to save time. And then when you run, maybe you want to go for the cheaper option. So for example, if you go in the cloud, it's probably cheaper to get 10 instances of CPUs than 1 GPU. Sometimes that's the case. Now let's see how it goes. Memphis, Tennessee, I think this is sports. Hopefully Royal Portrush, which considering first round, with temperatures, 603 strokes. I think it looks like sports, maybe baseball. If we have any sports people here, they can confirm. And our model says this is sports news. But as you can see at the output, and this is the last thing I'm presenting, we didn't do directly the answer. We did the label of the predicted text, and then let's see what's this. The label is in here. So we have an association between numbers and some human readable labels. And in general, as I go back, machines work with numbers. We don't always work with numbers. Sometimes we do, sometimes we don't. So in the real world, sometimes you'll have to do some additional parsing, either for the computer or for ourselves when we read the output to get what's happening. You can also find the example and run it on your machines with this link, or if you go with PyTorch text classification. On the internet, you have a lot of samples. You'll need Python You'll need Visual Studio Code or Jupyter to run it in an interactive way, and you'll need the dependencies, PyTorch and Torch text. I think it's enough. And let's go back to the presentation because I have a few more important slides. Let's go back. Let me share. And then I think I did a whole screen, but it should work. Can you see the screen?
Yes, we can see it.
Thank you. So let's go back to understanding the network. It was a simple input layer, but our input was embedded, so we didn't have the words in English. We had the words in English transformed to some numbers because the computer goes to numbers. And then we put it in a linear layer, which means a sum. So we had those numbers, we summated over them with some coefficients, and then we had our answers for each class. So we get our answer for each class. So we think that it's sports with a confidence of 070. Then we think it's news with 020. Then we think it's the other class with 010. So we'll pick in general the highest chance, and then this is our classifier. We did our demo as we expected. Thank you. This was mine. And for the questions, I'll also leave this one on the screen. It's a feedback form, so you can help me with feedback for my future sessions. And now it's time for any other questions that you have.